Hello everyone, I'm Yujeong from KAIST. Today I'm going to talk about Paris and ELSA. This work is done with my colleague Yunseong Kim and Professor Minsoo. In recent years, machine learning has shown enormous performance in various real-world problems. Consequently, ML plays an important role in many web services and is widely used in our daily lives. However, a challenge exists in providing efficient machine learning inference service. During training process, training servers build large batches with a readily available dataset to achieve high GPU utilization. However, unlike training, inference cannot achieve high GPU utilization. Main reason for such low resource utilization is that inference services should meet Service Level Agreement, SLA in short. As inference servers cannot use large batches that can saturate brawny compute resources of modern GPUs, inference servers suffer from low utilization. Although guaranteeing low service latency to end users is important to web service providers, low utilization of inferencing is problematic as it is interpreted as high cost. In response to the GPU underutilization issue, recently GPU vendor NVIDIA has released a reconfigurable GPU architecture. With the help of such architectural support, one big brawny GPU can be reconfigured into multiple small GPUs. The figure illustrates the architecture of NVIDIA's A100. Here, GPU's compute resources can be partitioned in the granularity of graphics processing cluster, in other words, GPC. A memory subsystem can also be partitioned. Each partition has a slice of alto cache and DRAM. In this example, the GPU is reconfigured to have 3 small GPU instances. Here, red GPU instance consists of 2 GPCs, and yellow instance consists of 1 GPC. However, how to configure GPUs in an inference server is not obvious and requires careful consideration to maximize GPU utilization due to the pitfalls of one-size-fits-all partitioning. First, model-agnostic partitioning cannot achieve high GPU utilization. For instance, while compute requirement of BERT is high enough to saturate a 100 GPU, compute requirement of MobileNet is not high enough to saturate brawny A100. In this case, we could increase utilization of MobileNet with small granular GPUs. As shown in the example, there is no silver bullet partitioning for all models, and each model's unique properties and its compute memory requirements should be considered. Also, even if model characteristics is considered, homogeneous partitioning is not optimal in achieving high GPU utilization. When the same model is executed on the same GPU, utilization can be significantly varied depending on the batch size. In this example, we can optimize GPU utilization if we use a small granular GPU for small batches and large granular GPU for large batches. As such, this observation motivates the need of heterogeneous GPU sets to increase GPU utilization. The problems of partitioning policies mentioned earlier motivate the need of a model characteristics-aware heterogeneous set of GPUs in an inference server to fully maximize GPU utilization. In response to this, we propose Paris and ELSA that can improve resource utilization for ML inference. The framework consists of 2 parts. Paris, by considering model properties and batch size distribution, partitions GPUs in an inference server. As the partitioned GPU instances are heterogeneous in their compute capabilities, it is important to schedule requests in accordance. Thus, ELSA considers the compute capabilities of each GPU instance to schedule inference requests at runtime. Let me first explain how Paris partitions GPUs into heterogeneous GPU instances to maximize GPU utilization. The partition process is twofold. First, Paris finds the best partition size for its bit size that can maximize GPU utilization without an SLA violation. Then, Paris calculates how many instances of each GPU size is required and partitions GPUs accordingly. Let me first discuss how Paris finds the best GPU partition size for its bit size. The graph shows GPU utilization when executing MobileNet on small, medium, and large-size GPU instances as we increase bit size. As the graph shows, if we use smaller GPUs, we can achieve high utilization. So to maximize the utilization, we would like to have small instances to service all queries to improve utilization. However, we made an observation that utilization and latency are highly correlated, and high utilization is not always beneficial as it can cause SLA violations. In this graph, we plot the latency and utilization of MobileNet as we increase bit size. When utilization starts to saturate, latency increases steeply. And such steep increase in latency can cause potential SLA violations. So here, based on the observation, assigning bit size larger than B1 to small GPU partition would lead to SLA violation. So, to maximize GPU utilization while preventing SLA violations, Paris assigns queries with the bit size B0 to B1 to small GPU instances, B1 to B2 to medium GPU instances, and B2 to B3 queries to large GPU instances. Now, we need to decide how many instances of each GPU size should be populated within the inference server to be able to service all the incoming requests. Paris utilizes bit size distribution, which tells how many queries of each bit size arrive at the server within a second. As explained earlier, its bit size has the best partition size. In this example, Paris decides to service incoming requests highlighted with gray, blue, and green boxes with small, medium, and large GPU instances, respectively. To derive how many instances of each GPU size is required, Paris utilizes throughput characterization table, which contains the information of how many queries each GPU can process per second based on profiling. Here is an example of how Paris determines the number of each instance. According to the bit size distribution, the server should be able to process 20 bit size 1 requests in a second. A small GPU can execute 20 bit size 1 requests per second. The inference server needs 1 instance of small GPU. Then the inference server needs 2 instances of medium-sized GPU, as 1 medium GPU instance can process 10 requests per second. In the same way, the server would need 2 instances of large GPU to service bit size 3 and other 2 instances of large GPU to service bit size 4, summing up to a total of 4 instances of the large GPU. As now the server is partitioned with a heterogeneous set of GPUs, we are going to discuss how ELSA, elastic scheduling algorithm, dynamically schedules requests to the partitioned GPU instances. To prevent SLA violation, scheduling algorithm should be able to predict the completion time of each query when scheduled to its GPU instance. ELSA predicts the query completion time by summing up the predicted execution time of queries that are queued inside the task queue of the target GPU instance. We use profiling to get a precise estimation of each query's execution time. Now let me explain how ELSA utilizes completion time prediction to prevent SLA violations and how ELSA maximizes the utilization of heterogeneous GPU sets with an example. In this example, An inference server consists of 3 instances of GPUs, 2 small GPUs, and 1 large GPU. Let's assume a situation where query A arrives to the server with its SLA target. Based on the prediction algorithm discussed in the earlier slide, ELSA can predict that assigning to which GPU instance will cause an SLA violation. Among GPU instances that do not cause SLA violation, ELSA intelligently selects the smallest GPU instance to improve GPU utilization. Again, when query B arrives at the server with its SLA target, ELSA predicts the completion time on each GPU instance to filter GPU instances that do not lead to SLA violations. In the case of query B, ELSA schedules query B to instance 3 as it is the only GPU instance that can execute query B without an SLA violation. To evaluate the effectiveness of Paris and ELSA, we implemented multi-GPU inference server on Amazon P4D instance having 8 NVIDIA A100 GPUs. In terms of benchmarks, we chose a wide selection of popular vision, language, and speech recognition models. In the remainder of the presentation, we will elaborate on the effect of Paris and ELSA on tail latency and throughput. For more detailed evaluation settings, please refer to our paper. First up is Paris and ELSA's impact on tail latency. In this chart, we plot tail latency as we increase the input traffic to the inference server. Input traffic is shown on the x-axis, and resulting tail latency is shown on the y-axis. Here, we compare Paris and ELSA against 3 baselines. Each series is a combination of partitioning policy and scheduling algorithm. We do not partition GPUs in GPU no partition. GPU max is the partitioning policy that we found by manually searching through all possible homogeneous partitioning points in a brute force manner. FIFS scheduler is a widely used scheduler in popular ML inference servers, where a newly inserted inference query is scheduled to any idle GPU available in the system. Without partitioning, tail latency increases steeply starting from the low traffic due to low GPU utilization. If we partition a large GPU into multiple small GPU instances, we can achieve much lower tail latency under the same input traffic thanks to the better utilization. See the vertical dotted line in the MobileNet chart. Under the same input traffic, tail latencies are significantly different. Paris, which systematically partitioned a brownie GPU into heterogeneous granular GPUs that perfectly suit for the compute requirements of incoming queries, can also drastically reduce tail latency. However, Paris can achieve even lower tail latency when combined with the heterogeneity-aware scheduling algorithm, ELSA. Paris and ELSA can even achieve 17 times lower tail latencies than best-performing homogeneous partitioning policies. Thanks to Paris' automated algorithm that systematically finds out the optimal partitioning points, and ELSA's heterogeneity-aware scheduling, Paris and ELSA achieve significant throughput improvement than other baselines. To conclude this talk, we propose Paris and ELSA, an elastic scheduling algorithm for reconfigurable multi-GPU inference servers. Paris and ELSA significantly reduces user response time and improves utilization by systematically partitioning GPUs and leveraging heterogeneity-aware scheduling algorithm.